And then now the next thing we're going to do is our forward simulation. So I'll just very quickly go through what we're doing, but we're going to, we'll have our regular PyLithApp.config files, and then for the forward problem, we're going to have this eqsim.config file. And it is referencing the spatial database that gives us what our earthquake slip is. So if we look at this, PyLithApp.config, maybe I'll get it, I can put it in the middle. There again, there's our journaling. Again, we're giving a qubit mesh reader. We're telling it what our mesh name is, the one that we just generated. This is just an optimization thing. You can have PyLith reorder your mesh so that it optimizes the matrix structure. So we're having it do that. We have a coordinate system spatial dimension of 2. Our PyLith problem, now notice that this says problem and not time dependent, has a dimension of 2. We're using a normalizer length scale of 1 kilometer. Internally, PyLith normalizes everything. And so depending on the spatial and temporal scales of your problem, you may decide to change the default values. This one, I believe, fine resolution is on the order of a kilometer, so we've changed our normalization factor to that. The relaxation time, we're setting that to a second. This is just a static simulation, so it's not going to do much. But we're going to run it for a total time of 0 seconds, time step size of 1 year. And then our only material, we just have a single elastic material. So it's an array of one material, and it's going to be elastic plane strain. Coming down, defining the properties for that material, we give it a label, elastic material. The ID number is 1. That's the only one that we have in qubit. And then the properties are defined in this mat elastic spatial DB. So that's going to be constant material properties. And then the database label is elastic properties. And then again, we have to define our quadrature. So Fiat simplex, dimension of 2. And then now we're coming down to our boundary conditions. These are, again, the very simple zero displacement boundary conditions, so that we're just pinning everything normal to the orientation of the boundary. So for x pos and x neg, we're pinning the x degree of freedom, and then for the y neg boundary, pinning the y degree of freedom. So then coming down, we have a single fault. So we have our interfaces is an array of a single fault, which we've named fault. This is the ID number is, we gave it an ID number in our create.bc file. If you remember, you when you define a node set, you give it an ID number and a name. So this ID number was 100. Oh wait, no, let's see, that's not right. The ID, no, that's just what we give it within PyLith. Yeah, never mind that. That's our internal ID number. We need that for Green's functions. The label is the name of the node set in qubit. And then new to this version of PyLith, we actually make use of the definition of the fault edge. So this edge is a single vertex, which we can actually see it up here. We go to fault edge. It's that node right there. That's the edge of the fault. So that defines the node set for the fault. And give it our quadrature, Fiat simplex. It's one-dimensional. since it's just a line. And then we're going to just define our out. Now in this case, before the example, we had the domain and we had the ground surface. Now we're adding a new one here, which we're calling points. And these are the points where we're going to compute the solution ground surface. And so we have to tell it what type of output that is. And so we give it this points corresponds to PyLith mesh.io output solution points. And then the ground surface is the same thing we had before. That's output solution subset, which is like one level up. Then we tell it what type of output to provide for each of these. In each case, we're going to use HDF5 output. It's just easier to work for the domain, the ground surface, output points. Now here, it doesn't yet know what points we want to output the solution. So we have to give it some information, first of all, about the coordinate system for our points. The coordinate system has a spatial dimension of 2, and the units in our coordinate system are kilometers. This is just our HDF5 output, but there's now a points.txt, and that contains the actual points where we want the solution. We can look at that. Is that big enough? Okay, so this is all it is. This is all just comments describing it, and then there's our list of points. So this is our x coordinate. We're starting negative. We're crossing the 0 to positive. You'll notice that all of the y coordinates, they're just slightly below ground surface, and that is to prevent interpolation, round-off problems where if PyLith thinks it's above, it won't be able to interpolate to that point. So we just put them slightly below the surface, 10 to the minus 6. So anyway, so that's how we do that. That's the points where we're going to compute the solution that we're going to use for our inversion. Okay, so we've done that. And then it's just our regular, we're not dealing much with the, we're not dealing at all with the stress and strain here. So we're telling it not to output any information for the state variables. And then again, we have HDF5 output for the fault and for the elastic output. And then this is, again, our PET-C parameters, which I believe are pretty similar to what we had earlier. Then the file that we have, let me see if I already have it up. No, it's, let's see, what's it called? EQ, no, it's, yeah. Oops. Okay, forward problem, and we're just giving it a little extra information. We're telling it cohesive kinetic fault. We have a EQ slip spatial database which we can look at. We're telling it to use linear interpolation for that slip, and then we give it a label. The slip time is just uniform, and it's t equals 0. And then out here, we're providing the names for our forward model simulation. So it's EQ sim, and then ground surf, points, fault, and state variables. So the slip distribution, which I just looked at, what was it called? EQ slip. Okay, it's just a pretty simple one here. We have, let's see, so we're slipping from, this is in terms of z, so we have 2.5 meters of slip from the fault down to 12 kilometers depth, and then at linear, since we're using linear interpolation, it will linearly taper from 2.5, what units are we? Oh, meters of slip down to 0. Actually, okay, so that's a typo there. That's because up here is what matters. We told it that our units were meters. So that is what our slip distribution looks like. And okay, so when we did that, we created all of the, actually all the other stuff too, but we created all these EQSIM files here that are here. So I don't know if we need to look at that right now. I think I'll generate the Green's functions first. So then for the Green's functions, in addition to the PyLithApp.config, we have what's called Green's functions.config. It's read automatically when we switch the problem type to Green's function. See right here, this is the command you're going to run. This we'll be running that, but first we'll just so the first thing that you see, that fault ID that we defined in PyLithApp.config, we use it here in the Green's function file. So we have that right. And then we're switching our type from, it was cohesive kinetic before, and now it's fault cohesive impulses. So that's our fault type. So these are going to be impulses that we apply along the fault. And then we're only going to do this for degree of freedom 0, which is left. In this case, it's reverse slip. The other option would be fault opening, but we're not going to consider that for this problem here. So then we have a database that we're going to use that tells us where we can allow, where we're going to apply the impulses. So we give it a label, and the name of that file is impulseamplitude.spatialdb, which we can look at in a minute. This we're just going to use nearest neighbor interpolation, because the reason is the impulse amplitude, in this case, we just give it like all ones, except for where we don't want it to slip, then we can give it 0. So you don't really need to do any sort of interpolation for that. And then again, we have our output information. So this is all going to be prefixed with the name Green's functions. Then we have it for ground surface, points, fault, and then for our state variables. Amplitude is really simple. It's the only parameter is slip, so it's a value. We're doing it in meters. We're providing 2 locations so that we can truncate the slip at 18 kilometers depth. And so we have a data dimension of 1, data is specified along the line. Our spatial dimension is again 2. We're going to use kilometers, so we have this conversion factor. And then all we have is x-coordinate, which is, just center of the mesh down. And then so that means that from 0 to 18 kilometers, we'll apply -1 meter of slip as our Green's functions. And then below that, we'll have no slip at all. So to run our problem, our Green's functions, oops, I think, did I have a, yeah. Oh, yeah, you're right. That's what the problem is. Okay, so that generated our Green's functions, and we can see what they look. So let's see. We'll look at we'll open the fault, and we'll look at the points for right now. So let's, huh? Oh, I didn't buy it. Well, I didn't see it. Okay, so, oh, that's interesting. We do it, I'm getting mixed up with that. Okay, there's our fault. There's the points where we computed the solution. Let me make everything bigger. So we'll make the fault thicker. The points will make bigger. And we'll, okay, we'll say look at the x component of displacement. So that's for the points, and then we'll look at the slip. So you can see our impulses are right here. So there's our first one, and you can see what the horizontal displacement is as a result of that Green's function. You could switch if you wanted to look at the vertical component, but we'll stick with horizontal. So anyway, you can go through all of the Green's functions you've generated if you so desire, and you can see what the response is. Let me rescale those. As you go through it. So that's all our Green's functions are. It's just the unit response, or the response to a unit impulse down here on the fault. And so you can look at this on the whole ground surface, but these are the points that we're going to be using for our inversion. So, all right, so let's get back. So the next thing we're going to do is actually do our inversion. Have a very simple Python code that does this, and we can look at that in great detail, but you can just kind of see how these things are set up. So the code is this invert py code. That's the command that we'll be using to do the inversion. Let's open it up over here. Oh wait, is it at a high? Oh, it's at the higher level. Yeah. Okay. So this is it. NumPy requires H5Py to be able to read the files. And so the first thing we do, here's a function that all it does is reads the impulse and response information from the Green's functions files that we just generated. We get the units, we get the slip that we applied for the impulses. Then we come down. I do some sorting because if you notice the impulses, they kind of jumped around on the fault, so it's nicer to sort them in a kind of, I can't remember which way I sorted it. It must be, I think, negative to positive. And so, so that is our impulses. So all we've got from that is the coordinates, the slip that we applied, and then we just reordered it so that it goes in a normal sort of order. Then we read the responses, which is just the displacements at the points at the surface. So again, we get the coordinates of those points, and then we just get the displacements. And then we have to, again, sort these because they're ordered in terms of the impulses we applied. So we have to sort those using the same sort key. And so that gives us our impulses and responses. Then we have a function to get our fake data. So that's another HDF5 file from our EQSim simulation. Again, we get our coordinates. We get our displacements at those points, and then we close the file. This is just getting command line options. Okay, and this is what we actually call those functions. So we get the impulse coordinates, the values, the response coordinates, and their values from this function. Then we get the observed coordinates and values using that function. And then, okay. We apply different penalties for the smoothing that we use. In this case, it's just minimum moment smoothing, which is just difference from 0. And so I have a file that just lists is the weight that you apply to that. So
this is like
it's just
no.
no. It's just a list of weights. So we start off hardly weighting it at all, and then we gradually increase the weight that we're applying to our penalty function. That's all it is. It's
weighting some observation.
No, we're not doing that.
So what weight goes?
It goes for your penalty parameter. This is when you're that inversion that I showed, we have a priori we have to it, which in this case is just
you're weighting your
we're weighting an augmented part of the matrix, because what we did was we decided that our a priori values are all 0, and then so it penalizes it for deviating from 0. So that's stupid sort of thing, but you can get more complicated with it's regularization is all this is. Yeah.
Right.
Yeah, except that it's just a diagonal matrix. Yeah.
So you're weighting
No, we're yeah. We're let me find it. Where is that? Oh, whoops! It must be down here. Okay. So we have that here. So it's just a parameter, is what it is. So this is our Green's function matrix. And then these, in this case, D is our a priori values are 0. And so we're just saying how much we're going to penalize it for deviating from 0. The solution, not, right? Yeah. It's, well, I think a misfit is fitting the data. Or D is a priori information, just saying that we think that it's 0. It's like probably the simplest assumption you can make, but typically what would be better, and I think I recommend this as an exercise for the reader, is to replace this with like a Laplacian type thing. That would be, then you're enforcing smoothness rather than, deviation from 0. So, so that's what that is. So that's just how much weight we're giving it. But as Rowena would point out, we didn't add any noise to our data, and so it doesn't really matter. But that's another exercise for the reader, is to add some noise.